Hello and welcome to Fouraye Education. Today's topic will be from vector calculus, the Nabla operator. So the Nabla operator can be seen as this symbol and usually is used in this form as the gradient operator. First of all, what is the Nabla operator? The Nabla operator can be seen in 2 or 3 dimensions. It is usually shown as a column vector of partial by partial x and partial by partial y. And this is the case for 2 dimensions, where in the case of 3 dimensions, we would have partial by partial x, partial by partial y, and partial by partial z. There are many uses to this, the most common being the gradient operator. Usually the gradient operator can be seen, used in the directional derivative and all that kind of things. So the 3 most common uses of the Nabla operator is the gradient operator, as mentioned before, or grad. You could say grad f or Nabla f or del f. The symbol is del or Nabla. It doesn't matter what you call it. You could also have the divergence operator, which is div f, and this would be shown as a cross product of Nabla and f. So to show it better, it would be partial by partial x, partial by partial y, cross product with f, and usually f is a vector field. And in this case, we would have partial of vector field f by x plus partial of vector field f by y. And this would give us a scalar quantity. Now we'll be talking about what these mean, what these values mean. But for the third use of the Nabla symbol, first of all, is the curl, which is the cross product between a vector field with the Nabla operator. It can be shown as curl f as well, and it's just this. So we just do vector cross product with another vector field. So to start off, we could start off with the gradient operator. The gradient operator which is shown as Nabla, or as I like to say, we apply Nabla over to f. So we have an f of x, a function or a scalar field, and then we apply the column vector Nabla over it, so it would get us this. Or more precisely, in this case, it would be f of xy, since we would be applying this to a multi-variable function rather than a single variable function. Now we have this. Of course, this is f of xy. I wrote it wrong, but yeah. So to give an example, what the gradient function gives is we enter a function or a scalar field, and it will give us a vector field with vectors pointing into the direction of the most largest number. So assume a vector field 10, a scalar field 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. And then inside we would have 5, 5, 5, 5, let's say. If we take the gradient of this, we will see that there are vectors coming from 5 towards the 10s. A better example would be something like 5, 5, 5, 5, 5. And then let's say 6, 6, 7, 6, 6, 5, 5, 5, 5, 5. So this is a scalar field. Turning this into a vector field, the 5 would point towards the 6. But eventually, they would all point towards 7, 7 being the maxima. So how do we apply these to functions? In functions, if we have a three-dimensional function, something like this, I couldn't draw it very well, but we would have arrows pointing towards that. So if we would make it into, if you look at it from above, from a bird's eye view, you could see something like this. So assuming that there's global maxima around here, then there would be arrows pointing towards that point. And let's say this is a global minima, arrows would be pointing outside. That this applies to both global and local maximas or minimas. It's a pretty basic use of the Nabla operator. And well, to make it simpler to visualize, I usually think of, again, applying the Nabla over the F. So we're not actually doing anything here, we're just inserting the F into the Nabla. So any value xy would input out this vector. The other use of the Nabla operator is the divergence. Divergence is very closely related to gradient, as can be seen with the further on when you take the divergence of the gradient, we would call it the Laplace operator, which we'll further on see. So the divergence is going to take in a vector field and give out a scalar value. And this scalar value is going to show whether the point inside this vector field is going to be a sink or a source. Or it looks at if it is diverging or converging. If it is diverging, then it will give a positive value. If it is converging, then it will give a negative value. So if we assume a vector field, let's say something like, let's say this, then this, in the case of the gradient, we can think of this as a maxima of a function. But when we look at it, from a divergence perspective, this is what we would call a sink. So the divergence in this spot, it would be negative, since it is converging into a single point rather than diverging from it. And if it is diverging from it, then it would be considered a source. As such, it would have a positive value. And computing the divergence is also very easy. We just take Nabla, partial by partial x, partial by partial y, and take the dot product with the vector field, usually. And then we would get this, which would give us a scalar value again, determining whether it's a sink or a source. Now the third and final, per se, use of the gradient or the del Nabla operator is the curl operator. The curl operator is a cross product between Nabla and a vector field. It will give out a vector when inserted in a vector field. Curl, as its name suggests, looks at whether things curl around a point or turn around a point. So how we compute curl, as mentioned before, is a cross product between Nabla, a vector cross product between Nabla and F. So all of these actually just kind of work similarly, per se. we just do different operations on we do different operations with the column vector Nabla. So in this case, let's say something like this, and then we have a vector f, fx, fy. So then we would do a cross product, so partial by partial y, partial by partial f, partial fy by partial fx, minus partial fx by partial f by partial y, and hence we would take the cross product for the curl. What does the curl indicate is, say we have a turbine underwater, or like a wheel underwater, let's say. When inserted in, what we would get is a vector up or down, indicating the direction of the curl. But usually, as we see in the two-dimensional case, it's going to give us a scalar value again. Partial by partial fx by partial fy by partial fx minus partial fx by partial fy would give us a scalar value, and this scalar value, if the scalar value is bigger than 0, it's usually counterclockwise rotation. Lesser than 0, it would be clockwise rotation. But again, with the topic of it giving us vectors, what we could imagine it as is, if the vector is positive, it's going to turn counterclockwise. The magnitude of the vector it gives is positive, it's going to turn counterclockwise. And in the case it gives a negative magnitude for the vector, it's going to turn clockwise. And that's the basic logic behind the curl. So for the gradient operator, we put in a scalar field and get a vector. For the divergence operator, we put in a vector field to get a scalar field. If you put in the whole vector field, we would get a scalar. But if we put certain values, we would just get a scalar value. For the curl, we insert in a vector field and get a vector field. Again, the vector field, as mentioned, is just going to give us the direction of the turn. And finally, the last topic I want to talk about regarding the Nabla operator is the Laplace operator. The Laplace operator is the combination of the gradient operator and the divergence operator. The Laplace operator is shown as the upside down Nabla, or Nabla squared. Hence this we can understand that it's Nabla times Nabla f. Usually, we take the divergence of the gradient. What happens if we take the divergence of the gradient? Then we'll find out how likely a point is to be a minimum. So if Laplace f is positive, then f evaluated at that point tends to be small. If it is negative, f evaluated at that point tends to be big. So let's assume a coordinate system. And let's assume a couple points. We have this point, this point, this point, this point. Now we will be drawing vectors. So we can think of this, let's say we have a multivariable 3D function. three-dimensional function f of xy. This I just drew would be the gradient of f of xy. Now we would want, now to take the Laplace operation, we would like to evaluate the divergence of this. So looking at here, this point would have a negative divergence since it converges and it is a sink. So this point tends to be a maxima and tends to have big values around it. And this point would have a positive Laplace, and in terms of divergence, it will be a source, so it would tend to be a minima point, a local minima, and it would have smaller values. So that is it for the Nabla operator or del operator. To sum it up, it has three basic uses: the gradient operator, the divergence operator, the curl operator. The gradient operator, as its name suggests, gives us the gradient, but on top of that, it gives us a vector field where the vectors are pointing to the bigger points. And in the divergence function, it gives us a scalar field which shows whether points tend to diverge or converge. With curl, it shows us it gives us vectors which show the direction of rotation around a point, and the combination of the divergence and gradient operators, the divergence of the gradient or Nabla squared or the Laplace operator, tends to show us how much of a minimum point something is. So we insert in a scalar field and get another scalar field, but it is a process scalar field showing which points tend to be smaller. The more positive values will give us, will show that around that point, more smaller values can be found, while the negative values would show that around that point more larger values. So that is it for the Nabla operator. Thank you for listening.